So in this problem we have a circular loop of rope of mass big M and radius big R, which is caused to rotate at a constant angular velocity omega. Now in part A of the problem, a small kink is introduced into the loop, and we're asked to find the subsequent wave speed that is caused by introducing the kink relative to the loop. So let's start off with our equation for the wave speed. So that's going to be given by the force that causes the wave motion divided by the linear mass density of the material that is propagating through, which in this case is going to be the loop. So the force that causes the wave motion in this case is going to be the tension force in the loop. So in this figure we've drawn an isolated segment of the loop. So here we've got the loop, which is subtending a total angle 2 theta, and there's a distance big R away from the center of the loop. Now for small theta, the tension force on each side of the isolated segment is going to be equal, which means that the horizontal components cancel out. Therefore, the net force on the isolated segment is going to be the sum of the vertical components of the tension forces, and that force is 2 times F sine theta, and for small theta, sine theta is approximately theta, which means our net force is approximately 2 times F theta. Now that's going to be equal to, by Newton's second law, the mass of our isolated segment, which we'll call little m, times its acceleration, which is given by omega squared times the radius big R, since the isolated loop is moving in circular motion. So here you see that the mass is going to be given by the length of the arc times the linear mass density. So by geometry of a circle, the arc length is going to be given by r theta. So the total length of our segment is 2 times big R times theta. So sorry, this should be big R. And that multiplied by mu is going to give us our mass for the isolated segment. So the total net force is 2 big R theta times mu times omega squared times big R. So now, if we isolate for the force, big F, we get that the force is 2 theta mu omega squared big R squared over 2 theta, which is just mu times omega squared times big R squared. Alright, so that means that the wave velocity is going to be the square root of mu times omega squared times big R squared over mu, which is the square root of omega squared times big R squared, which is just omega times big R. So that's our answer for part A of the problem. Now in part B of the problem, we're asked to figure out what the wave speed is relative to the laboratory. And we're asked to consider the wave speed in both directions. So we know that the loop is going to be rotating at a constant angular velocity omega. So if the wave is propagating in the same direction that the loop is rotating in, then the relative velocity compared to the laboratory of the wave, we'll call that v1, is going to be equal to the speed of the loop, which is omega times big R, plus the speed of the wave relative to the loop, which is, again, omega R. So we get that one possible speed for the wave is going to be 2 omega r relative to the laboratory. Now, if the wave is traveling in the opposite direction that the loop is rotating in, then the relative velocity is going to be omega times big R, which is the velocity of, or the speed of the rotating loop, minus the relative velocity of the wave relative to the loop, which is going to be omega r, which means that the second possible speed of the wave relative to the laboratory is just 0. So our two possible speeds for the wave relative to the laboratory are 2 omega big R and 0.